Hello, this is Jack Jackson. In this video, we're going to talk a little bit about getting started with working with these axioms a little bit. And the first thing we have to realize is there's a challenge for some students even understanding exactly what some of these statements are saying, such as those in the various postulates and propositions that we looked at earlier. And part of that is because the language of geometry is a little bit different than maybe some other part of mathematics that you may have studied. So let's see if we can complete these exercises that follow and before we move on to check our answer. So what happens here is most of these statements that might be postulates or propositions in various geometries is that they're often stated in a form, say, such as the ones that you see here in these exercises, but they're really if-then type statements, conditional statements, if hypothesis, then conclusion. And it helps if we can rewrite them in that form and recognize that they are if-then statements, or possibly if and only if statements in some cases. And so we need to write them in the right form, or in that form, in the if-then form, so that we can see identify the hypothesis and the conclusion. Okay, so here's some exercises. In the following, if the following is an existence postulate, if it just says that something exists and it can't be rewritten as an if-then form, then just say that. Say it's an existence postulate. Otherwise, rewrite the statement in if-then form. So I'll give you 4 exercises here, and then we'll go on and go over the solutions to that. But try to see if you can do it yourself first. Number 1, there exist at least n points. Okay. And I probably should just say exist is plural, of course. Exists is singular. Depends on what n is, I guess, how that matters. But n is a specific number, natural number. Say n might be 2. So there exist at least 2 points. Number 2, there exist at most n points. Number 3, there exists a line containing any pair of distinct points. Number 4, 2 distinct lines intersect at exactly n points. Again, just n is just some number. So rewrite these in if-then form if possible. If it's not possible, then just say it's an existence postulate. Pause the video when you think you've got solutions written down on paper, then start the video back up and then see how you did. Pause now. Okay. The first one is actually an existence statement. There exist at least n points. We're in some specific number. This just flat out says something exists. This guarantees the existence of at least n points, whatever n is. So there may or may not be more than n points, but there cannot be fewer than n points in the geometry. So if say n is 5, there exist at least 5 points. Then this says that there's 5 points in the geometry. There might be more than 5. Might not be more than 5. We don't know about that, but there have to be at least 5. Number 2, there exist at most n points. This is not an existence statement. This doesn't guarantee that anything exists. There might be no points at all. So we don't know that this doesn't guarantee the existence of points. It's not an existence statement. It's an if-then. One way to say it is if there exists a set of points, then the cardinality of that set is less than or equal to n points, obviously from this geometry. So there exists at most something is not an existence statement. Okay. It doesn't guarantee the existence of anything. On the contrary, it actually prevents the existence of too many things. If the empty set satisfies the statement, it's not an existence statement. So there could be an empty set of points in the geometry that would satisfy there exists at most n points. 0 points is at most n points. Okay, another way to say this is to put it in a form that would be actually more useful is this. If there exists a set of n distinct points, then the set contains every point of the geometry, which means if there are no other points to that besides those n points. That's the way it's probably useful to be used. Number 3, there exists a line containing any pair of distinct points. If the word a is replaced by at least one, the meaning is not changed. There exists at least one line containing any pair of distinct points is the same thing as saying there exists a line. So there exists a line means at least one, okay? So notice that here you're actually starting with the points and you end up with the line. So the hypothesis is that A and B are distinct points. The conclusion is that there's at least one line containing A and B. So we might say that is, if A and B are distinct points, then there exists at least one line containing A and B. Notice how I introduced arbitrary names A and B in the restating the statement. That's something you probably should do when it's convenient. And once again, this statement starts by requiring you to have a set of distinct points, and then we reach the conclusion there's at least one line containing the pair of points. There may or may not be additional lines containing that pair of points. We don't know. There's at least one. If there's only one point of the geometry, then this statement is true vacuously, so it says nothing, right? If you don't have 2 points, this doesn't tell you anything. But if you've got at least 2 points, or if you've got 2 distinct points, then there is a line containing them. Number 4, 2 distinct lines intersect in exactly n points. Okay. This one is actually just flat out false regardless of what you put in Euclidean geometry, but some other geometries it might be true. So if L and N are distinct lines, then there exists exactly n points in the intersection of the 2 lines, or on both lines. Okay, so notice that this requires that any 2 lines to have a non-empty intersection. So this means that there are no parallel or skew lines in the geometry. They don't even exist. And it requires the size of the intersection of any 2 distinct lines to be a set of exactly n points. No more, no less. So for example, if n is 1, this says every time you pick 2 lines, there's exactly 1 point in common. Or maybe n is 2. Any 2 lines, there's exactly 2 points in common, so forth. So here we're not concerned whether or not these statements are true in Euclidean geometry. Some of them are, some of them aren't. But these might be postulates or proposition in some geometry, maybe not Euclidean geometry. In fact, let's see here. Certainly Euclidean geometry, there exist actually infinitely many points, so no matter what you put in for n is, that's true. There exist at most n points. That's not going to be true in Euclidean geometry because there is no upper bound to how many points. There are actually infinitely many in it. There definitely exists a line containing a pair of distinct points. In fact, not only is there at least one, there's at most one as well. So that's a true statement in geometry, Euclidean geometry. But statement 4 is false. There are parallel and skew lines in Euclidean geometry, so there are lines that don't intersect at all. So again, these may or may not be true in Euclidean geometry, but they also may or may not be true in other geometries. Another thing that we have to do sometimes is negate a statement. So we want the opposite of a statement. In other words, we want to see what does it take to make that statement false. And so see if you can write out the negation of the following statement. It will depend on the geometry whether or not the given statement or its negation is true. And again, don't hesitate to give objects names in your answers. So it might be helpful to rewrite the statement as an if-then statement before trying to negate it. So here's the statement. See if you can rewrite it as an if-then and then write down the negation. 2 distinct lines intersect in at most 1 point. Press pause, work this out, and then come back. Press pause now. Well, another way to say this statement is if L and M are lines, then either they do not intersect or they intersect in a single point. So what would be the opposite of that? See, this is for any 2 lines that are different. Okay, I guess I could say, but distinct, meaning different there to be explicit about there. So the negation is there exist distinct lines L and M such there are at least 2 points in their intersection. Okay, so what this says, the first one says if L and M are any distinct lines, right, then they do not intersect or they intersect in a single point. Okay, so all it takes to make that statement false is to find one counterexample, one pair of lines so that they have at least 2 two or more points in their intersection. Okay, so it's a universal statement for all or for any, even though that wasn't actually stated that way. Okay, and again, we do not need this to be false for every case. So it could be such that there are two lines that don't intersect, or there's two lines that intersect in a single point. That's fine. For the negation, all it takes is one single place, maybe more than that. That's okay. But you don't have to say that all lines L and M intersect at least 2 points. All it takes is one counterexample. All right, we'll give an example of writing a proof in our next video.